I'm from IBM Research, and my talk today is going to be about lessons from using Pytorch compile for inference in specifically our Llama 2 model implementation. So why Llama 2? Well, first of all, it's currently being used by our clients already, and it's important for us to that our clients run this efficiently. It's important that we can make in general large models like Llama 7TB or even bigger models run efficiently for us. And for this purpose, we decided to collaborate with Pytorch and make an open source efficient implementation of Llama. So the issue we found is that when we tried the Llama implementation that's open source and available on on GitHub, we found it was hard to combine all these new optimizations that Pytorch 2 or 2.1 have been offering into single model for inference, right? So we combined things like the basic torch.compile, we added SDPA, we added Tensor Parallel, and we added CUDA graphs. And as I mentioned, this is open source, so please look at the QR code or look at the link we just put in here. Either of them, it will bring you to our GitHub repo that we just open sourced last week with our Llama 2 implementation. Now, first of all, I'll talk about what the performance numbers look like. And as you'll see, the green and the red are the compile plus SDPA numbers. And as you can see, for most of the models, compile gets you at least a 2x improvement in performance. And for 7TB, which is the model we run with Tensor Parallel and 8 GPUs, adding CUDA graphs gets you an extra 50% performance on top. So basically, you go from in 7TB, you can see 140 milliseconds per token down to 30 to 40 milliseconds per token, depending on your batch size and how much sequence length you're running with. Now, you will notice that the advantage from using SDPA, and in particular Flash B2, is not that big, and in some cases actually you get worse performance. If anyone here has read the Flash decoding blog post published a few days ago, they explain exactly why that's the case. But basically, it's because flash attention is not parallelizing in the right way for inference. But one of our next steps is going to be probably working out with them and just getting this new flash decoding technique implemented in our model to get this extra performance from SDPA that we should be getting. So what do we do to make all this stuff work, right? First of all, as people mentioned in the keynote, the most important thing to make compile get your models faster is making sure you have no graph breaks, right? So the Llama implementation in GitHub had one main issue, which was that the rotor embeddings, which are run in every single layer, use complex numbers, and complex numbers are not currently supported in Doctor. That meant we had to re-implement the rotor embeddings using basically modmulls and operations that are supported in Aten and in Doctor to make sure that our code had no graphics. Then another important thing for us was being able to choose which SDPA implementation to use. We want to make sure we can choose Flash 2 or memory efficient or the unfused implementation to be able to do relation studies, for example, the plot I just showed. And we learned that using the context picker, usually something like torch.CUDA.sdp backend, something enable Flash, that will not work without graphics either. So we had to also look at how to do that without graphics. And finally, when we got everything running, we realized that there was a bug in compile that does a new way to compute the guards for making sure the modules in the code do not change over each iteration. It was causing everything to recompile on every call. So basically, instead of having one kernel compilation or 3 kernel compilations if you're compiling with dynamic, we would have 500 compilations or n compilations if you're running n times. For SDPA, once we managed to get Flash 2 running, we also found another issue that was that every time you change the size on your inputs or your KB cache, you would be recompiling. It's wait, am I compiling with dynamic? But then we found that Flash specifically, and not any other kernel for SDPA, was actually forcing static compilation. Ed Yang fixed that issue for us a week ago, and it's been working great since then. For Tensor Parallel, first of all, we tried using D-tensors, but then we realized that the D-tensor implementation in Pytorch did not have support for torch.compile, which I think is not longer true as of like the last 3-4 days. I think it just got merged. But of course, when we were preparing this presentation, we had to like implement our own Tensor Parallel implementation that was compatible with torch.compile, right? Because again, what we want to do here is combine all these optimizations in one, right? So what did we do? We used the functional collectives that people have been mentioning, like all this new like work on the Pytorch distributed work on the keynote. And we had to like look and like, fix a few issues with the inductor way, like how the inductor actually compiles these things. Like there were some issues with memory layouts. We created cases like race conditions. There were some issues with like asserts triggering graph breaks that we had to fix as well. And in the end, we got everything without graph breaks. Finally, we were like, okay, we got all the numbers for like 7B, 13B. Everything was working great results. And we were like, okay, let's try 7TB, right? 7TB with Tensor Parallel and everything. It was like, okay, there's clearly some overhead on the CPU, like from launching all these collective kernels that's causing issues for us. So let's try CUDA graphs, which is the solution that everyone recommends when you have like too much CPU overhead, right? And when we tried, we just started hitting like segmentation faults, out of memory errors, and like one solution we found is that the KB cache, which is an input to our model, needs to be enforced to be contiguous. But there's still some issues that we will be working out, and I'll talk about it in the next slide. So next steps. Well, as I just mentioned, D-tensor compile support just landed on Pytorch Nightlist, so that's the one thing we'll be trying next. Another one thing that we want to try is currently all this work that we just built, all this model, like, only works for inference because the code only compiles without graph breaks using Torch no grad. We're actually looking for a fix for that, and that's the issue on GitHub that is tracking that progress. At some point, we want to be able to like, use our lab implementation for training, not just for inference, and that's basically one of the main blockers for that. Elias, on his talk like 3 minutes ago, mentioned that there's like this CUDA graph issue, like where like every kernel invocation takes 65 kilobytes. The Llama 7TB model has 80 layers. Each layer has like about 6 to 7 kernel invocations. So if you have like all these invocations and you invoke your model with like different sizes and different like shapes and everything, like 1,000 times, like 1,000 different shapes, or like 4,000 different shapes, depending on your context length or whatever, you will get your CUDA, like your graphics card memory like filled pretty fast. So we need to look at solutions for this. And as I mentioned, there's all these like segmentation faults and stuff we have been finding, which we also need to work on. Finally, we want to ensure that keep adding optimizations to this model, and some of them were already mentioned in presentations today. Like we want to add nested tensor support. We want to make sure that we can try all these like new D-tensor optimizations that make Will Console was talking about all these optimizations for the matmul and like the all-gather pattern that we definitely have in this code here. So we also want to make sure that we can take advantage of that. We want to try things like quantization, of course, page attention, all these new like inference optimizations that people are talking about in the last few weeks, and with always like making sure that everything is compatible with what we already have. So finally, our conclusion here is that we have decided to like invest in Pytorch and make sure that any optimizations we make are, as far as we can, contribute back to the core Pytorch. And that's why we open sourced our lab implementation. That's also, we also showed that if you are careful in designing your models, you can like add performance from different optimizations. Although it takes some work to make sure everything works together, which is like this whole composability theme. And then I would like to also thank all these people from Meta and IBM who basically I'm here presenting this, but like all these bug fixes, all this work's been like, would not have been possible without every people in here like reviewing PRs, making code, writing code, ensuring that everything works together, helping us like debug code, make sure everything is there, and like ready for like me to show here today, right? And with this, I'm pretty much done. If you have any questions, feel free to ask. Although I know it's almost lunchtime, so yeah, thank you. Yep.
Yeah. So thanks for sharing. So seems like most of the work is general enough, but not IBM hardware specific. So how to translate these work to the IBM hardware? Does that mean the IBM programming model seems like the CUDA or some other?
Right. So I don't know how much I can share about it, like about IBM specific hardware. Like my bosses are here, so they can maybe like say yes or no. Okay, we can take it offline, I guess. But I can answer like I can explain later if you want. Yeah.